Hello, everyone. We are excited to have you with us for this webinar. My name is Joshua Kroll, and I'm the Director of Sales and Marketing with Vexia Diagnostics. I want to welcome you all to this presentation regarding the plasma methylation profile by doctors' data. I'm joined tonight by my colleague, Dr. Wayne Sedano, the Director of Clinical Support and Education with Vexia Diagnostics, and a very special guest, Dr. David Quigg, the Vice President of Scientific Support with Doctors' Data. Dr. Quigg will be presenting a functional assessment of essential methionine metabolism and the plasma methylation profile. We are delighted to host this live webinar event with Dr. Quigg. Now, for those of you who don't know, Dr. Quigg received his BS and MS degrees in human nutrition from Virginia Tech and his PhD in nutritional biochemistry from the University of Illinois. He was then a research associate at Cornell University for 5 years prior to serving as a senior cardiovascular pharmacologist with a major pharmaceutical company for 7 years. For the past 42 years, he has performed and published research pertaining to nutrition, environmental medicine, and chronic diseases. As I mentioned earlier, Dr. Quigg is currently the Vice President of Scientific Support for Doctors' Data, where he consults with medical practitioners about recent biomedical research, the interpretation of laboratory test results, and treatment options for their patients. Now, without further ado, Dr. Quigg.
Well, thank you, Joshua. It's certainly a pleasure to be here, and welcome everybody. As Joshua said, we're going to talk about functional assessment of methionine metabolism with focus on a very specific test. So there is going to be a good bit of biochemistry, and I know that makes a lot of people wince, but I'm going to try to keep it as applied as possible. So what we're going to do is we're going to take a hike down methionines metabolic paths. We're going to be highlighting the methylation and transsulfuration processes. Too often that gets left out when we're focusing on methylation. Now, methionine is really a rather unique essential amino acid. It's actually my favorite in that it contains both methyl and sulfur moieties. Now, when incorporated into a protein, the methionines can provide important antioxidant protection to that protein, not to the rest of the body. But much more interesting is the multi-path metabolism of the free amino acid methionine. Methionines methyl and sulfur groups make it a very important precursor of several essential metabolites. How important? Well, from jump, its first downstream metabolite, S-adenosylmethionine, or SAM, our friend SAM, is so important that 50% of the methionine taken up by the liver is in fact incorporated, converted to SAM, the methyl donor. But much can go wrong while we're going down these paths, whether we're going down the south path, the southeast branch, or one of the loop back paths. And those disruptions can result in an array of common adverse health conditions. So today we're going to review the clinically relevant metabolism of methionine so that you can appreciate why and how the functional methylation profile may help you provide targeted intervention towards positive clinical outcomes for your patients in need. So let's light this candle. Okay, so the first question is who? Who might this test apply to? Well, we see disordered methionine metabolism in a number of neuropsychiatric disorders, everything from anxiety, depression, ADD, OCD, addictions, bipolar, and autism. Also see issues with the developmental delays, cardiovascular and vascular disease, Parkinson's disease, issues with inability to conceive and even pregnancy losses, immune dysfunction, and one of my favorites, impaired detoxification, where we end up having a net retention of xenobiotics, both metals and chemicals. So why? Why are we so focused on methylation? Well, The SAM-dependent methylation is so essential for a plethora of biological processes, including, but not limited to, the production of phosphatidylcholine. It takes 3 SAMs to make phosphatidylcholine from phosphatidylethanolamine. It's also involved in epigenetic gene transcription, that is the methylation of the actual DNA. And an example of that would be the serotonin transporter gene, where methylation of the promoter region turns on or off the production of that transporter. It's also involved in neurotransmitter metabolism, both biosynthesis and catabolism. For biosynthesis, the conversion of norepinephrine to epinephrine requires methylation, SAM-dependent methylation. And then on the breakdown side of the catecholamines, but also the catechol-O-estrogens, okay? And that's by catechol-O-methyltransferase. So we see the breakdown of dopamine, norepinephrine, and then the final breakdown from 2-hydroxyestradiol to 2-methoxyestradiol, which has very little activity. And then last, but certainly not least, and a focal point of this entire presentation is the metabolism of homocysteine, or the regulation of that. And if you don't remember anything else, just remember that methionine is methylated homocysteine, okay? And that'll jump out and hit you in a second. So who, why, how? How do we evaluate? We use a direct functional assessment, the methylation profile. And as the illustrious Dr. Jill James from the University of Arkansas Children's Hospital described it, it's an integrated metabolic profile reflecting the combined effects of genetics, epigenetics, diet, nutrient insufficiencies, and environmental toxicants. So we're not just looking at SNPs here and guessing. So some factors that can complicate the methionine metabolism, some lifestyle, alcohol abuse, some pharmaceuticals and quote recreational drugs, poor stress management, dietary extremes, severe limitations. An example here in the South would be an insufficiency of uncooked leafy greens. Tend to cook the bejeebers out of greens down here with some bacon fat. Nutrient insufficiencies, protein, B vitamins, folates, antioxidants, magnesium, and zinc. And some of those, particularly the magnesium and zinc, can become conditionally in greater need associated with specific SNPs. And then environmental toxicants can impose adverse effects on methionine metabolism via their production or induction of oxidative stress, both reactive oxygen and reactive nitrogen species. So what we do is we're going to look at the methionine and its downstream primary metabolites, and the very, very important methylation index, which is a ratio of methyl donor SAM to the methylation inhibitor SOL. And by knowing the basics of the metabolic pathways and knowing the peculiarities and favoritisms of the enzymes, we can spot bottlenecks. For example, if you're not going from methionine to SAM, we can figure out why that's happening. So we're looking for increased levels of precursors, lower levels of products. It's just basic biochemistry 101, and I'm sure you will fully appreciate that by the time we're done here. So I want to make a few comments about single nucleotide polymorphisms, or SNPs, because, you know, I'm not so much now as in the past five years ago. People were so hung up on SNPs, especially the MTHFR. But we have to keep in mind that the SNPs do not directly cause disease. They can affect enzyme function and efficiency. SNP expression can be modified, however, by diet, nutrients, and environmental toxicants. So it's not a death sentence to have a variant of MTHFR only. Which brings me to my second point is multiple SNPs in a given gene can increase the odds for abnormal phenotypic expression. For example, if one is homozygous for the MTHFR 677 as well as the A1298, you have a greater probability of decreased flow through that enzyme. And then finally, very importantly, SNPs in multiple genes for enzymes in a common process may be necessary to affect that metabolism and even health outcomes. Now, let me show you what I'm talking about there. So, people focus, they go to LabCorp, they go to Quest, they get their MTHFR, and then, oh my gosh, I'm homozygous, I'm heterozygous. What do I do? What do I do? It may not mean diddly to a tree. We have to look in the series of SNPs in these three different enzymes. And this is very important because the methyl group that's donated to homocysteine to get back to methionine, yes, it comes from 5-methyl tetrahydrofolate, but not directly. In fact, that methyl group is transferred to a B12 constituent of the methionine synthesis, MTR. Then that becomes methyl B12 that donates the methyl group to the homocysteine. And things, if everything's good, goes on up to methionine. However, this very important sister enzyme, MTHFR, provides repletion of the B12 after so many cycles or in the presence of excess oxidative stress. The cobalt moiety in the B12 becomes oxidized and it can no longer pick up that methyl group from the 5-MTHF. So through a reductive methylation process, MTHFR saves the day and rehabilitates that B12, if you will, so that everything can flow. So you can have perfectly normal MTHFR, but out of whack MTHFR and maybe even MTR, and this no longer has much significance because you create this bottleneck, which brings me to a very important clinical issue, which is called the methylfolate trap. And we want to prevent a methylfolate trap. So we want to make sure all these things are working. The methylfolate trap is nasty. I experienced this firsthand and it was absolutely horrible. Extreme anxiety, insomnia, quickness to anger. My wife didn't know what to do. Cognitive dysfunction. I mean, I'm MTHFR homozygous, 677. And so I took 800 micrograms of the 5-MTHF, thought like a typical American, hey, that was cool, let's double that. Well, when I doubled it, it took me 3 days to figure out what was going on, and talking to Ben Lynch to figure that I had created this methylfolate trap. And so what we do to prevent that is we prime the pump. We make sure that MTHFR and MTR, especially MTR, methionine synthase, is working. Provide B12, methyl B12 is pretty much the rage before throwing the 5-MTHF into a broken system, okay? So let's take a hike down from methionine, just so that we understand we're all on the same page with the way we go here. The first thing is methionine is converted to S-adenosyl methionine by our friend Matt, a very robust enzyme that can handle huge dietary fluxes of methionine. And then that S-adenosyl methionine drops off a methyl group to produce phoshatidylcholine, creatinine, which take up 70%, an estimated 70% of our total SAM production, but also, of course, for DNA, proteins, and neurotransmitters. After dropping off the methyl group, S-adenosyl homocysteine, via a bidirectional enzyme, becomes homocysteine, which is the major branch point here. So what happens at this point? The whole concept is to try to keep homocysteine low so it doesn't force this reaction north. And we do that by taking the southeast branch of the path, go down through transsulfuration, CBS, CTH, on down, making cysteine and glutathione. So that pulls from the homocysteine. And then we also have a couple of pathways to go back from homocysteine and complete the methylation cycle to remake methionine, the methionine cycle. So you might be wondering, okay, who decides? How is it decided? How does the body decide whether I'm going to go down through transsulfuration or re-methylation? Well, the body is extremely smart. And the level of SAM is the actual guide for hiking down here from homocysteine. When SAM is high and adequate, the body tends to stabilize the CBS, and we shuttle the homocysteine through transsulfuration and limit the activity of MTHFR. So it's a very, very slick system. It's not just working willy-nilly. Okay, so we have two pathways to get back from homocysteine to methionine. So let's first look at the folate-dependent long path, where we get our methyl group from 5-methyl tetrahydrofolate through MTR, and it just gets methylated back to methionine. So that's the long route, and this is the route where we can have more complications. Now, we also have the short non-folate dependent route of re-methylation, but this is only at the liver and the kidneys. So what happens here is the homocysteine shoots directly north via the enzyme betaine homocysteine methyltransferase using betaine trimethylglycine as the methyl donor to remake methionine to jump back in the pool and go through this whole process. Now, it's really important to realize that betaine in a supplement form is betaine anhydrous, which is absolutely not the same thing as betaine hydrochloride. I'm sure you're all well aware of that, but I've actually had people say, oh, I can just use betaine hydrochloride. If you do that to get enough betaine into somebody, you're going to blow out their stomachs. So beets is where betaine was first discovered, and hence the pronunciation of betaine. Beets are also a great source of folic acid, but we'd have to eat one heck of a lot of beets. Now, this reminds me of one of my favorite composers, musicians, producers, Roger Waters, who went off on his rant on the Wall album, where he said, you can't have your methionine if you don't eat your beet. How can you have any methionine if you don't eat your beet? Well, Roger wasn't a biochemist, and he was really talking about me, but you get the picture. Now, let's talk about some of the things that can go wrong in these complex pathways. From jump, as I said, we can block the conversion from methionine to that critical methyl donor SAM. And that happens as a result of insufficient magnesium, oxidative stress, lipopolysaccharide excess, inflammation, hepatitis B, C. And let's say we get past that step, that's all working good. Then we get down to SAW and homocysteine. Now, normally this reaction goes south very efficiently, but when homocysteine accumulates, it drives AHCY north. We get overproduction or accumulation of SAW, which is an incredibly potent inhibitor of all SAM-dependent methyltransferases. Okay, so the goal is to lower homocysteine, not just to reduce risk for cardiovascular disease and damage to the arterial endothelium, but to keep the whole methionine cycle functioning. How can we have problems with homocysteine? Of course, if we have insufficient folate, we're heading back up north. B12, again, I talked about. Zinc is involved in every docking of homocysteine to every enzyme. And then, of course, betaine, if we have a shortage of betaine, we can't take the short route. And of course, B6, insufficiency, we can't go down through transsulfuration. All those things could result in increased homocysteine, inhibition of methylation. We can have another issue, a direct inhibition of methionine synthase, MTR, with oxidative stress, excessive alcohol intake, and inflammation associated with high levels of TNF-alpha. So at this point, if you feel like you just got whacked in the head by a 60-mile-an-hour methylation tennis ball, don't be worried. We're going to apply it now into some case reports and sample reports. I've seen this look many times at conferences. So one of my favorite pictures. So reading the test report. First of all, the test requires an overnight fast. Now, this particular report is for a 16-year-old who had a major eating disorder, and never should an overnight fast result in a profile like this. But my point here is that we start our plot at the 50th percentile, and then as a particular metabolite is low, it goes to the left. If it's high, it goes to the right. So it's a normal distribution. But homocysteine, cystathionine, and the SAM-to-SOL ratio are one-tailed plots. So we start here, and as it gets higher, it goes out, except that the SAM-to-SOL ratio is an inverse plot. So while this is high, this is low. For the SAM-to-SOL, this is low, this is high, and we want a high level. So a level of 7.7 compared to 4 is in the green. And if we had a bad ratio of SAM-to-SOL, such as 2, it would fly all the way over to the side. It's a little hard to grasp because of a reverse plot thrown in there. But if you really can't grasp this, just look at the actual patient's result compared to the reference value. Okay, so let's look at a couple of cases here. My first case is an inability to produce methyl donor SAM, and it's never totally absolute, okay? And here we're talking about a problem with our friend Matt, methionine adenosyl transferase. Now, Matt is inhibited by magnesium insufficiency, like I said, infection, oxidative stress, and methotrexate, as well as liver disease. So what you see here is the bottleneck, increased level of the precursor at very low level of the product. And again, this is never zero. So there's still flux going through here such that we can still end up with too much SOL as a result, in this case, of elevated homocysteine driving the reaction north. Now, this particular individual, I forgot to mention, was a 50-year-old, very high stressed out person, high anxiety, high calcium containing antacid abuse, and IBS type D, so frequent diarrhea. So that combination of presentation really sets her up for magnesium insufficiency. But what about the increased homocysteine? What's going on with that? Well, that can also be related to the very low level of SAM, because we see sluggish methylation at the level of MTHFR not functioning properly when we have low SAM. Again, that's a SAM-dependent regeneration of that B12 or a low SAM-to-SOL ratio. So what would we do for this poor person? Okay. Consider magnesium, magnesium, methyl B12 to prime the pump, B6, then folinic acid or 5-methyl tetrahydrofolate, your choice. Now, the second case I want to talk about is actual impaired transsulfuration detoxification. This is a 57-year-old female, fatigue, cognitive decline, 5-year standing Lyme's disease, and retention of lead and cadmium based on provocation testing. So first thing we notice is she's converting fine from methionine to SAM. There's no elevated homocysteine to cause increased SOL to inhibit methylation. That all looks good. But look at her cysteine, very low. Cystathionine, a bottleneck, very high. What does that tell us? That tells us that transsulfuration pathway is not functioning well. And I actually looked at her red blood cell glutathione levels, and they were dismal at about 50% of the normal reference value. Now, so what we're talking about here, again, is a bottleneck. We see a high level of cystathionine right here and a low level of product cysteine. So that tells us where the issue is. We know the enzyme is CTH, and we know that with sluggish CTH variants, they require more B6. So I would definitely consider this person more B6, maybe even in the form of P5P. N-acetylcysteine and or a high bioavailable glutathione, because she's just not getting down there to make that cysteine, and her glutathione was very low. I knew this person quite well and took advantage of the situation, so to speak, and did a little pilot study on her using a single dose, 1 teaspoon of a high quality liposomal glutathione per day. And you can see at baseline, she was about half the reference value. After 2 weeks, she was up 40%. After 2 months, she was above the reference value of 1100. And by 4 months, 1 teaspoon of liposomal glutathione a day, she was well up above the reference value with a 154% increase. It's actually a really fun study in N of 1. But very well controlled. So I just want to emphasize as well that the transsulfuration products are not just glutathione and cysteine. We also make taurine in a two-step process. We don't make a whole lot of taurine. We're just a notch above the cap with respect to making taurine. But also very important, from cysteine, we get sulfite, and then with adequate molybdenum and sulfite oxidase, we get the essential sulfate. And in fact, it's been demonstrated in the literature, a well-controlled study, that liposomal glutathione increased plasma cysteine, reduced glutathione taurine, as well as essential sulfate in a group of 13 autistic children. So this next case is a really interesting one, and I'm sure Dr. Sedana will have some input on this one. This is a case where I call naive or benign abuse of synthetic folic acid, and there's also some impaired transsulfuration. This is a 62-year-old male, Parkinson's disease, very, very poor diet. His GP prescribed that he takes 7.5 milligrams of synthetic folic acid a day for his elevated homocysteine. So apparently he had a Quest or LabCorp homocysteine, and someone said, oh, we can bring that down with folic acid. The gentleman was also taking 1,500 milligrams of N-acetylcysteine per day. And that's not surprising, because we know that in a lot of these neurological diseases, we're hurting for glutathione, and NAC is a good way to try to get that up. So when this test report, either he was so well stocked with NAC, or he didn't follow the instructions to stop taking his NAC 48 hours before the test. So I'm not sure what to make of this high cysteine. I'm not worried about it. But you'll notice that his homocysteine was not under control with the 7.5 mg of folic acid. And that, of course, drove the reaction north, had a very high level of SOL and a dismal SAM to SOL ratio. So what's going on here? Well, look at the cystathionine. They would have never known this had they not run this panel. Again, the bottleneck in transsulfuration, just not able to make that glutathione And serendipitously, perhaps, something he read on the internet, he was taking the 1,500 milligrams of NAC to try to overcome that. So again, it's not just a matter of methylation we're looking at here, but also transsulfuration. So what do we do for this gentleman? I would consider definitely stopping the synthetic folic acid, especially at that dose. I would consider priming the pump on the upside of the methionine cycle, methyl B12, then introduce maybe 5-methyl tetrahydrofolate or folinic acid, betaine to help him with the short route, getting back out of the homocysteine accumulation, as well as B6 to try to help support his transsulfuration. But I'd keep him on the NAC. Now, importantly, we know that excessive unmetabolized folic acid, UMFA is fun to say, okay? Excess UMFA may disrupt folate metabolism, transport, and receptors. And I think what may be happening in this case is he may have also had a dihydrofolate reductase variant, which is at the very top of folate metabolism. And so just dumping in a boatload of folic acid, synthetic folic acid, didn't cut it for him. So again, I'm not entirely against synthetic folic acid. It helps a lot of people. It was a standard of care for lowering homocysteine. And quite frankly, I know this will stir some hornet's nests, but it's never been demonstrated that 5-methyl tetrahydrofolate or folinic acid are any more effective for the vast majority of people than folate, synthetic folate, for lowering homocysteine. Now, my last case is one of my favorite topics, and that's the MTHFR heterozygote syndrome. I've been to so many conferences, and I've had docs come up to me with their iPads and say, and they're all depressed and showing me their LabCorp or whatever lab's results of their MTHFR being a heterozygote, and they're just depressed. And I'd say, well, so what? I mean, come on. So here we have a case of a 47-year-old mom. I think she had 3 or 4 kids, major fatigue, anxiety. She found out that she was heterozygous for the 677 MTHFR, and she was new to veganism. So what do we see going on here? First, methionine is quite low, so it's not surprising that she's not producing enough SAM. She's just not putting enough through the system here. And secondly, she might have a high demand for SAM. We don't see any accumulation of SOL, which is really interesting. And this is an old report where we were measuring adenosine, and it was normal. Her homocysteine is not at a level that I would want to be at. So her transsulfuration is good. So what's going on here? Not only does she have an issue not producing enough SAM, but the homocysteine is accumulating. Her SAM to SOL ratio is not good. So what do we do here? Consider the diet. Increase protein, okay, and especially high quality protein. We need more methionine into this young woman. With anytime you increase protein, you have to increase B6, but you don't have to, you should. We want to give her some B12, methyl B12 to prime the MTHFR pump, and magnesium. However, in vegans, I've seen more vegans with taurine deficiencies because, again, we don't make that much taurine. It's not enough. We get the vast majority of our taurine from animal flesh. So you can give all the magnesium, you can give it IV, you can give it transdermally, you can give it orally, you can give it rectally. If you don't get that taurine status up, the cells are not going to be able to hang on to that magnesium and help every magnesium-dependent enzyme work. Maybe some PC to decrease her demand for SAM if it's in fact high, and folinic acid to make sure things are going back up in the remethylation process. But I want to emphasize that if she does increase her methionine intake, increase the flux through the system, it could very well be that this will go even higher. So in a case like this, if we improve the intake of the quality of the amino acids, more methionine, we definitely should consider retesting because of the higher methionine influx, which we already see that there's a little bit of an issue here, okay? So that's pretty much it. My takeaway points are really quite straightforward. Many patients present with symptoms or conditions that can be associated with disordered methylation, transsulfuration, or re-methylation. And so we want to look at the big picture, and that's provided by the methylation profile that provides a functional integrated metabolic profile reflecting the combined effects of the SNPs, other genetics, cofactor insufficiencies, and toxicants. We don't treat SNPs. Rather, we address the evidence-based phenotypic expression of a particular single nucleotide polymorphism. I'm not saying don't do SNP analysis. I'm just saying it's really rather difficult to guess, oh, the person has this SNP, that SNP. Therefore, it's not that straightforward. There's so many other factors impacting these variants of these enzymes and this gene expression. So we want to look at the actual biochemistry, the actual metabolism that's going on. And then when you do that, your results can facilitate targeted, efficient clinical intervention for each individual patient. So I thank you kindly for your attention, and I think at this point we'll go to a Q&A.
Excellent. Thank you so much, Dr. Quaig, for that insightful information. So we'll take some time to address some questions that have come up during the webinar. If we aren't able to get to your questions, or if you wish to follow up with us afterwards, please email us at info@abexiadiagnostics.com. And if you do have questions and you haven't typed them in yet, go ahead and do so in the window on the right-hand side there, and we'll get to them as we're able to. Let's start with this first one. So, Dr. Quaig, can one identify over-methylators from the test results?
No, you really can't. There was an incredibly elegant study that came out of Dr. James's lab. She's kind of a guru in this area. And there was a technician, and I hate to call him a technician, but he was a brilliant young man. And he did such beautiful kinetic studies of what's going on in a cell and determined very clearly that it is not the availability of SAM nearly as important as it is the elevation or the level of the inhibitor SOL, which binds with a much greater affinity. So when they jacked up the SAM in cells, they did not see over-methylation at all. That's tightly controlled. So the direct answer is no. This test cannot identify the so-called over-methylators. And usually when we're talking about over-methylation, we're talking about actual methylation of DNA, where you might see something like a methylation to non-methylation ratio in like a lymphocyte sample or something like that. But no, it does not.
Okay, excellent. That actually, it segues into another question that just came in that I think is applicable. So, when would you suggest supplementation with methionine versus SAM?
Versus SAM-E?
Yeah.
Yeah, SAM-E from a bottle. I'm not a real big fan of SAM-E in a bottle. First and foremost, I like to let the body do what it can best, especially with a background as a senior pharmacologist. I've kind of jumped that fence a long time ago. And using SAM-E as a drug, I think could be a last resort, or as a first resort to see if in a trial dose, if adding SAM-E directly is going to provide any relief, symptom relief, improve things. But I think in the long run, you would rather, if the person had a poor methionine intake, increase that methionine intake and optimize all those enzymatic reactions to make things better. That's my personal opinion on SAM. SAM-E in a bottle. SAM in general is a very unstable molecule. And I don't know how much SAM-E is people are actually getting if it's an old bottle of SAM sitting around. So not my favorite way to go. And it's not the cheapest supplement out there.
Okay, super. Would you say that there are any special instructions for patients or the clinicians when preparing for doing this test?
Yes, absolutely. And like I showed with the Parkinson's patients, stop non-essential supplements 48 hours before the blood draw. And it absolutely has to be a overnight fasted blood draw. So stop those NACs, stop the methionine supplementation, stop anything else that you're doing that's not essential. As far as for the clinicians, follow the instructions very carefully. You really need to follow the instructions very carefully, get the specimen as soon as it's spun down, get the plasma acidified so that everything is stable and valid when it gets to the laboratory. But back to the stopping the supplements, this is something I thought a lot about over the years. And in some cases, let's say someone has been on your intervention and maybe they're taking a couple of different supplements. Your question at that point might be, how are they now on this supplement regime? So it's not so black and white as to stopping or not. If it's a virgin patient coming in, not on any supplements, definitely, or let's start from scratch, see where they stand. But if you want to find out if your dose of folinic acid or magnesium or zinc is working, and that's something that the person takes every day and doesn't have a problem with, then I say, why disrupt homeostasis and take a step backwards? Let's be happy with the answer of, hey, with what you're doing, everything looks good, or not. Do we need to increase the folinic acid perhaps, or B6? Okay.
That's excellent insight, Dr. Craig. We've got a few more questions coming in. I did want to ask, what methodology is used to perform the testing, and how is it validated?
The methodology is liquid chromatography, LC, triple quad mass spec. And so it's state-of-the-art liquid chromatography. We used to call it HPLC, which stood for high-priced liquid chromatography, but it was really high pressure. But it's liquid chromatography with mass spectrometry, and the entire run is set up, optimized for sulfur-containing amino acids. So it's a little different than your standard amino acid run that doesn't do as well for the sulfur-containing amino acids. How is it validated? Thanks to the wonderful Dr. Jill James, who really developed this whole profile in her research laboratory. But in her research laboratory, the blood had to be drawn there, and specimens immediately flash frozen at -80. That doesn't lend itself to a remote laboratory. So she was kind enough to do a split with us on 50 different samples. She analyzed them directly in her lab, prepared the samples as we described, shipped them to us, and then we compared the results, and the results were really, really highly correlated with what she gets in her research lab. And then on top of that, you have your standard validation, your quality control, and all that. but that was the main thing. And as a result of that, we made a nice donation to the Children's Hospital's Research Center for her collaborative work.
That's excellent. So how would a patient be treated who has elevated SAW but normal SAM?
Again, typically there, what you're going to see is, why is the SAW elevated? And that's because the homocysteine is elevated because it's not going down through transsulfuration or not efficiently going back through re-methylation. So you want to fix the reason why homocysteine is accumulated. SAW won't just accumulate on its own. Remember, that's a bidirectional enzyme that normally goes south. But when homocysteine accumulates, it goes north. And there's your SAW accumulation, which is such a potent inhibitor. Now, there is one other thing that, other than homocysteine, you remember coming down from SAW to homocysteine, there is a release of adenosine. There are very rare cases, usually related to pharmaceuticals, maybe hypoxia, where you'll have an accumulation of adenosine. And that adenosine, like elevated homocysteine, can drive that reaction north and create excess SAW. And that's why the recommendations are always in there for magnesium and zinc, because the clearance of adenosine is driven by magnesium and zinc-dependent enzyme. We for a while, we were actually measuring adenosine, but it became a nightmare because most clinical centrifuges aren't spinning down the platelets hard enough. And we were just seeing a ridiculous number of very high adenosines. And we just said, this is not right. We're not putting out bogus data like this. So again, back to the original question, you're not likely going to see just excess SAW unless the downstream product, homocysteine, is elevated.
Excellent, thank you. So I know that Dr. Sedano has probably got some things that he would like to jump in and share, or have some questions. So I'm going to ask him to come off mute if he'd be so kind. I'm sure that he's got some things to input as well.
Yep, I'm here, Joshua. Thank you, Dr. Quigg. Wonderful. This is actually one of my favorite tests, and I wish it was functional medicine tests, and I wish a lot more people would do this test. For one reason, Doc had mentioned many times that you're looking at the functional analytes. In other words, the phenotype, the expression of whether there's a SNP or what is going on chemically, and this actually describes this really quite well. The test also, to keep it simple, one of my favorite parts of the test is to look at that SAM-SAW ratio. That's also referred to as a methylation index. And what that's going to tell you is the global methylation. What's going on with the methylation of the body? If you don't take anything away from this, hopefully, I'm sure you did, just remember that. Looking at that global methylation, looking at that ratio, and what that essentially is going to tell you is there adequate SAM supply, and is SAW being removed? And then from there, I think hopefully, Dr. Quigg, I see you shaking your head, yes, can kind of agree that you can start building right from that point, looking at that ratio. That's kind of fun, for me to take a look at. But you're looking at this thing functionally from the functional biochemistry.
Yeah, absolutely. Yeah, and a lot of people, that's the very first thing they look at is that methylation index. But if all we did was put out, okay, here's your SAM, SAW, and your methylation index, we would miss all that juicy stuff about transsulfuration and even the step down in the beginning from methionine to methyl donor SAM. So yeah, we need the whole picture.
Yeah, oh no, absolutely. But that's my first go-to is right there. What's going on with methylation? Is it hypo or is it hyper? I do want to just take a moment and talk about the hypermethylation of the DNA. To me, that's a totally different animal. And I don't want to get into details because I will be talking for about 3 hours on this, so I'm not going to do it. So here's, and I'm sure Dr. Quigg could do probably 10 hours on it. Here's the takeaway on that. When you hear about DNA methylation, either hypo or hyper, here's basically what happens, right? The methylation is what? The epigenetics, the genetic expression. What happens is that think about a cancer methylome presentation. It all starts out with hypomethylation, and the genes or the cancer genes become methylated. In other words, the genes of repair are now the ones that are methylated, they're turned on, but it all starts with hypomethylation. So that's the one takeaway I'd like to talk about, mention from that point on. So anyway, I'll turn it back over to Doc.
Oh yeah, and it's very different for different genes. Some genes are turned on when they're methylated, some genes are turned off when they're methylated.
Yeah.
So it is a very complex thing to deal with.
Yeah, the CPG sites, and we don't want to get into that tonight. Okay, they've had enough chemistry. Biochem.
Yeah.
Dr. Quigg, I'm going to ask one more question before we start wrapping things up. So, are the reference ranges specific to age or gender?
Yes, we looked into that heavily and worked with Dr. James on that. She did an awful lot of work with, 3 and 4-year-old children, usually some at some level on the spectrum. And when we compare our reference values for males and females, looking at all of our population data, we do not distinguish between the sex. But we do age dependent, and that's simply less than 18 or greater than 18. So unlike some of our other tests, they're not so broken down into, age 1 to 5 and all that sort of stuff. It's just not necessary in looking at these metabolites.
Okay, super. We actually had one more question slip in right here at the end. I'm going to try and squeak this in. Would you say that it's safe to take liposomal methionine without testing?
Liposomal methionine? No, nobody makes liposomal methionine, do they? No, you mean liposomal glutathione?
It's possible that was the question. I just wanted to make sure that I
methionine is so well absorbed, you don't need a liposome vesicle to get it into the body. I mean, it is a bit hydrophobic as far as amino acids go, but there's no issues with absorbing methionine. I think maybe the person really was referring to liposomal glutathione. That I can answer.
I think that was the case, yes.
Yes, yes. You absolutely can. I mean, it's not uncommon amongst my friends and colleagues to take a good dose of liposomal glutathione before you go into the sauna and mobilize a bunch of toxins. Just feed forward with that endogenous detoxification. And you will not find in the literature any indication of having excess glutathione being associated with any adverse conditions. The biggest factor would be the cost of the liposomal glutathione that's going to keep people from ODing. But I mean, the reference value is greater than 1100. You could get up to 2400 and there would be no adverse effects.
Okay, excellent. All right, well, we're close to time, so we'll go ahead and start to wrap things up. I just want to remind everyone that you can take advantage of clinical support from Dr. Sedano, who you heard from a little bit earlier. It's available through our free Ask the Doctor service, and he can address questions about patient scenarios, results, and testing. And now that we've learned about the benefits and clinical value that this test can offer, I want to just briefly review how to order them through our platform. First, you're just going to log into your Avexia account and click Avexia Link Lab Orders, and that's on the left-hand side of the dashboard. Next, you would select your intended patient or create and add a new patient. Then you would click Add New Lab Order and select Specialty Labs. Then add doctor's data products to order and search for the desired test. In this case, it would be the plasma methylation profile, and then add to the cart by clicking the blue plus symbol. Now, if you are drop shipping to a patient, you'll need to add the shipping charges under Add Shipping Miscellaneous Products to Order. Now, for those of you that are with us still, I want to let you know that fortunately we're implementing an update that'll be taking effect next week that's automatically going to add these charges for you. So moving forward, this will no longer be a manual process. You won't have to worry about adding that extra step and incorporating those shipping charges. It'll just show up in the cart automatically. So then finally, you're going to preview and confirm your order once it has been added to the cart and click place order. Just want to remind you that we're happy to assist with any issues or questions that you may have. We can be reached during our business hours between 8 a.m. and 8 p.m. Eastern Time at 888-852-2723, Monday through Friday. You can also contact us anytime via email at info@abexiadiagnostics.com. Just so I can say thank you again for joining us for this webinar event. Until next time, from everyone at Abexia Diagnostics, stay healthy, stay safe, and we wish you all the best on your pathway to wellness. Thanks, everyone. Thanks, Dr. Quigg.
Thank you.